Welcome to lecture 3 of module number 9. In this module we are discussing numerical methods to solve partial differential equations. What we have done in the previous lecture is introduce a couple of examples for partial differential equations of the various types. The one was the hyperbolic type of equation, parabolic and the elliptic type of equation, and we saw the numerical methods in order to solve each of those types of equations. So the examples we are going to take in today's lecture essentially are going to be one example of a parabolic equation and another example of a hyperbolic equation. So for hyperbolic equation we will take a transient heat transfer through a rod. For a hyperbolic equation we will take a transient plug flow reactor equation, and that is going to be dc by dt plus u dc by dx equal to k multiplied by c to the power 1.25, starting with c at time 0 and at all locations is going to be equal to some value c0, and that c0 we have taken as 1, and c at all times and at location x equal to 0 is also going to be equal to c0. And then we are going to track how, as the reaction takes place, how the concentration C changes both with location and with time. So that is going to be the example of hyperbolic equations that we are going to use, and the example of parabolic equation. This will be the heat transfer through a rod, the transient heat transfer through a rod example, and there we have partial T by partial T is going to be equal to alpha partial square T by partial x squared minus beta T minus T infinity. And for simplicity we will use the Dirichlet type of boundary conditions instead of Neumann type boundary conditions, and that is going to be the temperature at all times at x equal to 0 is going to be some T1, let us call that, and temperature at all times at x equal to L we will call this as some temperature T2, okay. And this is going to be our parabolic equation, and of course we also need initial condition in time, and T at time equal to 0 and all x is given as some temperature T0, okay. So these are the two examples that we are going to solve. We will start off with the parabolic equation example, and for the parabolic equation one of the methods we said that we can use is a finite difference method, in which we will use the forward in time central in space method. So forward in time central in space is going to be for parabolic the FTCS method is Ti comma k plus 1 minus Ti comma k divided by delta T is going to be equal to alpha multiplied by Ti plus 1 comma k minus 2 Ti comma k plus T I minus 1 comma k divided by delta x squared minus beta times T I comma k minus T infinity, okay. Now initially what we will do is we will solve this particular problem assuming that beta equal to 0, and then we will take up a problem in which we will take a finite value of beta. So the problem that we are going to solve initially is that there is a rod and that rod is kept, initially the rod is cooled at room temperature, okay, and all the ambient, that is T infinity, is going to be at 30 degrees also, okay, and this end we will say is kept at 80 degrees, this end is kept at 30 degrees, and we will solve two problems. First, in which there is a heat loss taking place from the rod to the surroundings, that would be this, actually that we will solve later. First we will solve the problem where there is no heat loss taking place from the rod to the surroundings, and if there is no heat loss, for no heat loss beta is going to be equal to 0, and if there is heat loss, then let us take beta equal to 0.002 second inverse. That is going to be the units for this beta that we are going to take, and alpha value we will take it alpha. So, for steel for example, alpha is going to be approximately 0.2 centimeters square per second. So, this is the value of alpha that we will take in this particular example. Okay. And let us take the length of this rod as 2 centimeters. So, we have this entire rod length going from 0 to 2, and we want to find out the temperature, how the temperature varies with respect to time and with respect to space. Okay. So, let us divide this particular region into n intervals, and n we will take in this particular case as 5. So, we will have 5 intervals. Okay. So, our delta x is going to be equal to 2 divided by 5, and that is basically going to be equal to 0.4. Okay. 0.4, 0.8, 1.2, 1.6 and 2.0, and the location I index will go from 1, 2, 3, 4, 5 and 6. Okay. And then this is going to be in the x direction, and likewise in the z in the t direction we will have various delta t's, and this is of the k that I will write, k will be 0, k will be 1, k will be 2 and so on and so forth. Okay. So, this is what we are going to do, and the condition for stability, and again we are not going to prove this, but okay. So, if we have the original equation as Tt equal to alpha Txx, that means we have, if we go to this equation, if we are just going to look at this particular part, the homogeneous part of this equation, if this is going to be our overall equation, the condition for stability is going to be 2 alpha multiplied by delta t divided by delta x squared should be less than or equal to 1. Okay. If this condition is met, our overall scheme is going to be stable. If this condition is not met, our scheme is going to be unstable, and to put it in another way, it is going to be delta t should be less than or equal to delta x square by 2 alpha, and delta x squared by 2 alpha is going to be equal to 0.4 squared divided by 2 alpha, and alpha value we took as 0.2. So, divided by 2 multiplied by 0.2. So, our delta t has to be less than or equal to 0.4. Okay. So, what we are going to do is we are going to take several different values of delta t, for the value of delta x taken to be equal to 0.4, for value of alpha equal to 0.2, for value of beta equal to 0. So, that is the first problem that we are going to solve. Then we will take a larger value of delta t and see what we mean by instability, and the third thing then we are going to do is take our delta t under the stable conditions, solve it using Microsoft Excel with the actual problem that we wanted to solve, that is with beta equal to 0.002. Okay. Now, I will rearrange this particular equation, and I will take this guy on to the right hand side. I will first multiply it by delta t, take this guy onto the right hand side and rewrite that equation, and we will get that equation as Ti comma k plus 1 should be equal to Ti comma k plus alpha delta t by delta x squared multiplied by Ti plus 1 comma k minus 2 Ti comma k plus Ti plus 1 Ti minus 1 comma k minus beta delta t multiplied by Ti comma k minus T infinity. Okay. So, this we can take Ti comma k along with rest of this stuff. So, we can have alpha delta t by delta x squared multiplied by Ti plus 1 comma k plus Ti minus 1 comma k plus 1 minus 2 alpha delta t by delta x squared, okay. This guy multiplied by T I comma k minus beta delta t T I comma k minus 30 was the value of T infinity. Initially we will take value of beta to be equal to 0 and value of alpha is 0.2, value of delta x is 0.4. Okay. So, these are the conditions for which we are going to use Microsoft Excel in order to solve this problem. We will take delta t equal to 0.1 and then we will take delta t equal to 1. For value of delta t equal to 0.1, we will show that the overall scheme is going to be stable because delta t has to be less than 0.4. For the choice of delta t equal to 1, we will show that the scheme is overall going to be unstable. Okay. So, that is the first part we are going to do, and in the second part what we will do is we will take the value of beta, we will change the value from 0 and we will take a more realistic value, and that value is going to be beta equal to 0.002 as we have written down over here. So, these are the three parts, the problem that we will solve in 3 parts using Microsoft Excel. So, now we are going to solve parabolic PDEs using forward in time, central in space method. We will write our alpha value was 0.2, we will write our beta value initially was 0, I will write our delta x values, the delta x value we took as 0.4 and we will write our delta t value, delta x value, and delta t value we will take initially as 0.1. Okay. What we need is we need to compute the value alpha delta t by delta x squared. So, we will compute that value also, alpha, so a into dt by dx squared, that value we will compute that because that is the coefficient that we will need multiple times. For example, if you look at the board what we had solved. Now, if you look at the equation that we have, then at several places we require the coefficient, alpha delta t by delta x squared over here, as well as we require the coefficient alpha delta t by delta x squared over there. As a result, we will pre-compute this particular coefficient alpha delta t by delta x squared so that we can use this forward. Now, what we are going to do is we will start off with a temperature of 30 degrees along the length of the reactor, that is going to be our initial condition, and we will use this particular equation in order to update those values at every time. Okay. So, that is what we are going to do, and let us go back to Excel and we will compute our alpha delta t by delta x squared, and that is going to be equal to, okay. So, let us now compute our alpha delta t by delta x squared, and that is going to be equal to this multiplied by delta t divided by delta x squared. Okay. So, that is what we have as this particular value over here. If we were to use delta t equal to 1, that becomes 1.25, for delta t equal to 0.1 it is 0.125, that is the value of our A. So, now what we need is on the columns we will have the various temperature values along the length of the rod. So, I will have the locations I specified along the columns and k will be specified along the various rows. So, I will go along the columns. Okay. So, I is 1, 2, 3, 4, 5 sorry 5 and 6, that is going to be our i's. I will just make that centered, and we have initially at time t equal to 0. At time t equal to 0 all the temperatures are at 30 degrees. So, I will write all of them as 30. Okay. So, these are our initial conditions. Okay. And starting with initial conditions, now we go forward. As we move forward we will write these things down. Okay, I will move this one row below and I will actually write down the actual time and our actual x. I will write this. Okay, this is going to be equal to 0, this is going to be equal to the previous value plus delta x. Okay, and I will put the dollar signs over there because the delta x does not change. Okay. So, this is the length of the reactor, or sorry, the length of the rod going from 0 to 2 centimeters, and the time is going to be equal to previous value plus delta t. Okay. And I will again press F2 and put dollar sign, so that when we move, when we just drag it below, we will not have this value changing. Okay. So, what happens at time 0.1 is our initial condition changes, the boundary condition changes, at one end of the rod the temperature is suddenly made 80, and at all the other ends we have at the other end we have the temperature kept at 30, and we want to find out how the temperature changes for all the internal points. Okay. So, this is the temperature at this is going to be T I comma k is going to be equal to T 2 comma 2. Now, T 2 comma 2, if we look at the expression, it is going to depend on the values of at the previous time. It is going to depend on this value, it is going to depend on this value, and it is going to depend on this particular value. So, I will write that down as, now what we had was alpha delta t by delta x squared, this multiplied by T I plus 1 comma k plus T I minus 1 comma k. Okay. So, it is alpha delta. So, this guy is alpha delta t by delta x squared multiplied by T I plus 1 comma k, and this is T I minus 1 comma k. Okay. This is added to 1 minus 2 multiplied by alpha delta t by delta x squared. Okay. This guy multiplied by T I comma k. Okay. So, our T I plus 1 comma k, T I plus 1 comma k was going to be equal to alpha delta t by delta x squared multiplied by this guy plus this guy plus 1 minus 2 alpha delta t by delta x square multiplied by this guy. Now, if we had that beta term also, we will have that term coming in over there as well. Okay. So, we will just what we are going to do is we are going to put dollar signs for our alpha delta t by delta x squared, and then we can just drag it. Okay, and then we press F2, we will see this guy as alpha delta t by delta x squared multiplied by T I plus 1 comma k plus T I minus 1 comma k plus 1 minus 2 times alpha delta t by delta x square multiplied by T I comma k. Okay. That is what we will get for the entire row. So, let us take this entire row and copy it, say up to time 5 or something, or time 1 or something. Okay, no, this is incorrect. What I need is, okay, what I will need is one more row, and then I can move it down equal to the above value, and this one is going to be equal to the above value. Okay, and this one I will just drag it downwards, and that is going to be my temperature that we get at the time 0.2, and we just drag it at several locations. Okay, and we go up to say time t equal to say 5 or something like that. Okay. Okay, and I will just delete this. Okay, so now what we have is we have the temperature at various locations in the rod as the time progresses. So all these values that we have over here are the values of temperatures at various time, varying with various time and various spatial locations. So these are the temperatures varying with time and space. So what we will do is we will try to plot the overall temperature profile at various times along the length of the rod. Okay. So what we will do is we will select these guys as our temperature values. So insert, we will do a scatter plot. Okay, and we will just delete this, we will delete this as series 1. Okay, so this is going to be our plot for our temperature, which are all 30, changing with the location, and I will just go here and increase the font size so that the things are fairly visible. Okay, so this is the temperature at the initial point. Now what we will do is we will add some more data, select data, we will add a series. Now what we need is the x values, these are going to be the x values, we will need the y values, and the y values we will have them at time t equal to 1 second. Okay. So this is going to be how the temperature looks like after 1 minute, sorry, after 1 second, not 1 minute. Okay. Then we will have the temperature value along the length of the rod at the end of 2 minutes. So the y values should be these guys, and the x values are going to be this. Okay, and we will add one more series that would be at the end of, we will just add one more at the end of 3 minutes, or sorry, at the end of 3 seconds, that is going to be this particular row, and the x values, corresponding x values are at this row. Okay, and we will add one more series at 5. Okay, so let us go up and look at the plot that we have obtained. We will go there, right click, format axis, and we will start the axis at say 25, and we will end the axis at say 85. We know for sure that the temperatures are not going to go beyond 25 and 85. So that is what we will do, and format data series, and we will add lines. Okay, what we will just add lines so that we can see. okay, this is going to be the fourth line, and then finally the fifth line. Okay. So, this is the temperatures along the length of the rod at so these are the temperatures along the length of the rod at the initial condition. These are the temperatures at along the length of the rod at after 1 minute. These are the conditions along the length of the rod, and I will add a line over here also. Okay. Okay. So, so this is how the initial condition is, this is how the final temperature is going to look like, and this is how the temperature is changing at each time along at various times along the location in this particular rod. So, that is how the solution evolves, this is how the solution is evolving in time, and this is how the solution looks like in space at various different times. Okay. So, this is the solution that we get when we have started our system at t equal to 0 with using our delta t value of equal to 1. What happens, let us see, when we change the delta t value equal from 0.1, we change the delta t value to 1, and this is what is going to happen. We will just look at the various times at 0, 1, 2, 3, 4 and 5. At 0, this is the I'll just go right click, format axis, and I will have the minimum and maximum as automatic. Okay. And we will change the data . So, this is the data at 5, this is going to be I will just change the data, and this is going to be the data at the end of 3 minutes, this is going to be the data at the end of 2 minutes, and the data at the end of 1 minute, and this is the initial data. Okay. So, this is what we get. So, at initial conditions we had this temperature, and you can barely see it, the temperature was at 30 degrees. At end of 1 minute, again the temperature is still well behaved, we have 80 degrees, 30, 30, 30 and so on. At the end of 2 minutes we have 80, 92 degrees becomes the next temperature. Now, the temperature cannot rise beyond 80. So, this 92 degrees that we see is definitely incorrect. At the end of 3 minutes the temperature goes negative. So, at one end of the rod the temperature is kept at 80, at the other end of the rod the temperature is kept at 30. There is no way how the temperature should actually go below 30 degrees or should go above 80 degrees, but that is what our model gives. And at the end of 5 minutes we have the temperature predicted as minus 400 and plus 600, and if we look at what temperature is being predicted at 50 minutes, we have, or sorry, not 50 minutes, 50 seconds, we have temperature predicted as 10 to the power 27, 10 to the power minus 10 to the power 27, so on and so forth. So, what we have seen is that when we go to delta t equal to 0 from 0.1 to 1, we get from stable solution, we will move on to the unstable solution. What happens when we take this delta t equal to say 0.5, again we will get some kind of an oscillations, and finally this, so the temperature is going to be unstable. That is what these temperatures show you. So, these temperatures are clearly, we are going on to unstable region. And what happens when the delta t is kept at 4, exactly equal to 4, we will get the temperature to be stable. Okay. The temperatures are not unstable, but the temperatures are indeed stable when delta t is 0.4. What happens when we go at 0.42 is we will get some kind of oscillations, if you see over here, and if we go to long enough time you will see that the temperatures indeed are tending to diverge and not converge. We started with temperatures of 56 initially, and then they are going to 70, and they are hovering around 69 and 70, so on and so forth. So, just to recap, we take a delta T greater than 0.4 and we will get our temperatures to be diverging, and if we take the delta T less than 0.4 we will see that the temperatures are indeed converging at the end of our simulation. Okay. So, that is what we have seen using the forward in time central in space method. I will just press delta Z several times so that we get our final solutions. Okay, this was what our solutions were at for delta x equal to 0.4 and delta t equal to 0.1. Okay. So, I will just include the other temperature also in the final boundary I had not included. So, we will just move this. Okay, and same thing we will do with other temperatures as well. Okay, so this is how our solution looks like when we have beta equal to 0, we take our delta T small enough so that we get convergence. Now, when we change our beta from beta equal to 0 to beta equal to 0.002, we now need to go and change our equations that we have put for the expressions, sorry, that we have put for these conditions to include the effect of beta as well. So, we will go here, we will press F2. Now, this is without the beta term. Now, if you look at the board, the beta term that we have is, now we need to include beta multiplied by delta T multiplied by T minus 30. Okay. So, that is the term that we are now going to include. Okay. So, minus, if you we had just seen, now minus beta multiplied by delta T, which was over here, multiplied by the temperature at I comma k, which is this guy. K, remember, over here is equal to 1, our I is equal to 2. So, I comma k is going to be this guy minus 30, 30 was the temperature of the ambient. Okay. So, we will just put dollar signs over here, $B, $3, because the beta value, the cell for the beta value is not going to change, the cell for delta T is also not going to change, it is going to remain over here. So, we will put dollar signs over here as well. Okay. And we will just move this and copy it over here, and we will just go ahead and check one of the values. We will just drag them below and we will check one of the values. We will press F2 and check these values. This guy is going to be alpha delta T by delta x square multiplied by T I plus 1 plus T I minus 1 plus 1 minus 2 times alpha delta T by delta x square multiplied by T I comma k minus beta, that is over here, multiplied by delta T, that is over here, multiplied by T, that the temperature, minus 30, that is the temperature at the ith location, minus 30. Okay. So, that is the expression that we ought to get. So, we will select all this and double click, so that all the values below are going to change. Okay. And what we see over here, for that small enough value of beta, that beta does not affect the overall temperature profiles, almost, there is almost no effect on of beta on the overall temperature profiles that we get in this rod. There is only a very slight change. Now, let us change from beta equal to 0.002 to 0.01. Okay, and we see that temperatures have changed very much slightly, and then when we change that beta to 0.1, we find that the temperatures have changed quite a bit again. Okay. So, when beta was equal to 0, this were what the temperature profiles were. When beta we had changed to 0.1, this is what the temperature profiles are. Okay. So, what is happening when we change the beta really is, we are seeing the effect of heat loss taking place from the outer ends of the rod to the surroundings, and this is what effect we are going to get. Okay. So, what we have done now using Excel is basically talked about the parabolic PDE solving using forward in time, central in space method. The other methods for solving parabolic PDEs were central in time, sorry, were backward in time, central in space, and that is going to be a fully implicit method of solving. So, we have forward in time, central in space, which is going to be first order accurate in time. However, it is going to be an explicit method for solving these equations. The next method is going to be basically backward in time, central in space, which is a fully implicit method, and the third method that we had talked about was the Crank-Nicolson method, which is an implicit method, but it is second order accurate in time. Okay. So, those were the methods that we talked about for parabolic PDEs. I will just rename this particular sheet as parabolic and FTCS. What we will next do is we will do this exercise for hyperbolic PDEs, and I will just move or copy this particular sheet to sheet before. Create a copy, and we will retain most of it, however, we will change this to hyperbolic. Okay. And what we expect in hyperbolic system, hyperbolic equation is that we will get this system to not converge in this particular example, and we will go and look at that example on the board, and then we will try to solve this. So, the hyperbolic equation that we had was dc by dt equal to u dc by dx, sorry, plus u dc by dx equal to k c to the power 1.25. From the previous time, basically we had taken our k value as equal to 0.1, and our u value was sorry, our k value was equal to 1. No, I think yes, the k value was equal to 0.5 and the u value was equal to 1, and we were trying to look at the overall reactor of length 5 centimeters. So, the overall reactor was of the length 5 centimeters. The inlet concentration was 1 moles per centimeter square, and the inlet velocity was 1 centimeter per second, and our k value was 0.5 moles per centimeter cube to the power minus 0.5 minus 0.25 divided per second. That was the k value. Okay. So, for these conditions we will go now and try to solve this equation. Before doing that, we will just express this as we did before with parabolic FTCS. So, we have what we have over here is the derivation for the parabolic FTCS. We will do the same thing for the hyperbolic equation, and for hyperbolic we get Ci plus 1, sorry, Ci comma k plus 1 minus Ci comma k divided by delta t is going to be equal to minus u multiplied by Ci plus 1 comma k minus Ci minus 1 comma k divided by 2 delta x minus k multiplied by Ci comma k to the power 1.25. Okay. If we go back to this equation, actually I had made a small mistake over here. There should be a negative sign that should appear, because reaction, as the reaction takes place, the amount of the concentration of that the reactant starts getting depleted from the system. So, there should be a negative sign over there, which I had missed. Now, rearranging, what we will get is Ci comma k plus 1. Now, we multiply by delta t and we take Ci comma k on to the other side. So, we will get Ci comma k plus 1 should be equal to minus u delta t by 2 delta x multiplied by C I plus 1 comma k plus 1 minus u delta t divided by 2 delta x C I, sorry, that is not right, minus u delta t divided by 2 delta x multiplied by C I plus 1 comma k minus C I minus 1 comma k plus C I comma k minus k times C I comma k to the power 1.25. Okay. So, this is what we would be getting, and there should be a delta t term over here. So, minus delta t multiplied by this guy. Okay. So, this is the overall expression that we will get by doing the substitution. The initial condition is that the temperature is the concentration is going to be 1 throughout the reactor. The inlet condition is that the concentration is going to be equal to 1 throughout the reactor, and this is the equation that we are going to indeed employ in order to solve this overall problem. Okay. So, let us again go back to Excel and modify the PDE, the parabolic PDE Excel sheet that we had previously used for this hyperbolic equation, where again the values of u value was equal to 1, our delta t as before we will take our delta t equal to 0.1, our delta x in this particular case is going to be equal to 1 because we are going to divide length 5 into 5 intervals. So, from 0 to 5 we will divide it into 5 intervals. Okay, that is going to be our delta x. Okay. So, let us now solve this overall hyperbolic equation using Microsoft Excel. We will just modify the parabolic PDE using FTCS appropriately. Okay. So, let us look at Excel now. Hyperbolic PDE using FTCS. Now, what we have alpha, instead of alpha we have the velocity u and the constant k. The k is 0.5 over here, u was equal to 1, del x we have taken as equal to 1 and delta t we will take 0.1. We do not need alpha delta t by delta x square as we had previously. Okay. So, we will instead of alpha delta t by delta x square, what we need is u multiplied by delta t divided by 2 delta x. Okay, this is what we actually need. So, that is what we are going to compute. So, this is going to be equal to u multiplied by delta t divided by 2 multiplied by delta x. That is the value that we are going to use over here. Okay. And this are the x locations, and this is the actual length of the reactor that we have, and these are going to be the times, various times. Okay. So, I will just select this, and I do not want anything to be filled over here, and I will delete. Now, initial conditions throughout we had the 1 1 1 1 1 and 1. Okay, those were going to be our initial conditions, and what we have over here is basically at the inlet our values do not change. So, these are going to be the inlet conditions. Okay. So, we have the initial conditions over here, we have the inlet conditions in this particular row. Okay. So, now using the equation what we have is equal to minus u delta t by 2 delta x, okay, multiplied by we have this previous value plus the next value in the location. Okay. So, that is really what we are going to get over here, and use that value plus we will have Ci comma k minus k multiplied by Ci comma k multiplied by C delta t multiplied by Ci comma k is what we are going to get to the power 1.25. Okay. So, what we have over here is we have minus u delta t by 2 delta x multiplied by t I plus 1 comma k plus t I minus 1 comma k plus sorry, not t, it is going to be C I plus 1 comma k, and here we have C I comma k minus k, which is the constant. We should put dollar signs over here, $B, $3, that stands for this particular constant, and k multiplied by delta t, again we put dollars over here multiplied by concentration at I comma k to the power 1.25. Okay. And this is what we are going to get up to here, and at this particular condition we will have to really use some kind of a backward difference formula. We cannot really use the central difference formula simply because there is no boundary conditions that should be satisfied over there. So, the backward difference formula at this particular location is just basically going to look like minus u delta t divided by delta x. So, it is going to be 2 equal to minus, it is going to be 2 multiplied by this particular guy multiplied by Ci minus Ci minus 1 plus Ci comma k minus k times delta t times Ci comma k to the power 1.25. Okay, that is what we are going to get over here. Okay. Just made a small mistake, this should not be a plus sign, this actually should be minus sign, because that is what the derivative is going to be about, and that is what I ought to drag over here. Okay. So, these are the values that we have obtained, and let us just double click and just drag and drop. So, what happens over here is that the concentration values soon become negative. So, we have this as a negative concentration, here we get a negative concentration, here we get a negative concentration. As a result of this, soon we will have the overall scheme failing, but even before it fails, what we know is happening over here is we know for sure that the concentrations are going into negative, which is not a physical phenomena. So, what we see in this particular case is that the forward in time central in space method does not work for hyperbolic PDEs. Okay. So, this is where I am going to end today's lecture. What we have done in today's lecture is look at the forward in time central in space formula using Microsoft Excel and applied it to parabolic and hyperbolic PDEs. The thing we had said about the parabolic PDEs is we need to check the value alpha multiplied by delta t divided by delta x squared. Now, that particular value, if that lies between minus half and plus half, then our overall scheme is going to be stable, and if that lies beyond minus half and plus half, our overall scheme is going to be unstable. When we implemented that, what we found was that the delta t value has to be less than 0.4. So, we took several examples. In one case we took delta t value was 0.1, in another case we took delta t equal to 1, and in the third case we took delta t equal to 0.5. What we saw was for delta t equal to 0.5 and delta t equal to 1, the overall solution went to 10 to the power 27 or something like that. The temperature predicted by our code was 10 to the power 27, which are clearly not physically possible, they are clearly not numerically possible from this particular actual equations. Okay. So, what that means is that the numerical solution that we had used was an unstable method, the numerical method that we used was an unstable method for delta t greater than 0.4. Okay. Then we used a hyperbolic PDE, we used the same forward in time central in space method, and for delta t equal to 0.1 also we found that the forward in time central in space method does not converge. Okay. So, what we are going to do in the next lecture, and which is going to be the final lecture in our computational techniques course, is use the upwind method for solving the hyperbolic PDE, and we will see that the upwind method converges under certain conditions, and that is where we will end our discussion on PDEs, basically solving the parabolic and hyperbolic PDEs is essentially where we end our lecture series at, and then we will recap what we have done through all the modules in this particular course. Okay. Thank you and see you in the next lecture.